I'll talk about Cadre, where I'm the principal investigator and autonomy lead. It's a lunar technology demonstration of multi-agent autonomy that's being sent to the moon next year. Today's topic is primarily a collaboration with these fine folks, Drs. Rossi, Naka, and Albi. But I also want to give a shout out to the rest of the Cadre team that's working on the rest of the autonomy stack, on avionics, flight software, mobility, systems engineering, and many different areas that are all making our trip to the moon next year possible. But today, I'm going to, oh, there's a video. I'm surprised because it's supposed to be side by side, but here's at least a video of our rovers, how they perceive the world, and that's going to be relevant to the rest of the talk that I'm giving today. But you can kind of see that it's a fully autonomous rover that's perceiving the world, and it's planning path through that world, and it's trying to do this all in real time without having to spend a lot of time, driving a little bit, stopping, thinking, and then driving again. That is sped up, yes, slightly. So this is the slide I actually want to talk about, which was my overview, right? So I do want to talk about the technology demonstration, the fact that we've got 3 rovers and a base station. I think the really relevant part here is that our avionics is a modal AI's voxel. So this is a Snapdragon 821 4-core ARM CPU with an Adreno 530 GPU. And it performs basically all of our flight software functionality. It performs all of our autonomy and all of our multi-agent autonomy capabilities and functions. And our autonomy algorithms tend to have to solve large problems. So both in terms of the state space, or in terms of the maps that they're planning on, or in the environment that they have to deal with. So that can be expensive in compute time. And one of the things with Cadre's mission is that we're extremely time and thermally constrained, because we're on the moon for about 2 weeks to get our mission done. So that's a very short amount of time. And we're also going to the equatorial region of the moon, where it's extremely hot. So you can have a recipe for, you need to get what you want to do done quickly. So because of that, today I'm going to talk to you about how we used OpenCL to parallelize some of these expensive operations, and specifically in our formation driving algorithm, which basically figures out, if you have a number of robots, how do you drive them in a particular configuration to get their mission done. So I hinted at the fact that we're going to the moon. We're specifically going to Reina Gamma, which is this very interesting feature on the moon, where you have these dark and light regolith mixing together in these swirls. What we're going to be doing is to demonstrate that we can coordinate a team of robots, and specifically what they're going to be doing is some surface exploration, as well as some ground penetrating radar in a multi-static configuration. So they're going to work together to really explore what's in the surface and what's below the surface. And all that's going to happen sometime in the spring of next year. So just a little bit over a year from now. What makes our system very unique is that we've got these small rovers, and they have to go through these wake-sleep cycles, mostly because they are thermally and power limited. So they take in sun to recharge their batteries, and have a single radiator with just the surface, the top of the robot to radiate heat. And really, the key takeaways here are that we want to minimize the time to plan, because our cycles are short. So just to give you an idea, is we're expecting that during the lunar day, it can get up to like kind of the middle of the day, up to 120 C. That's extremely hot for our electronics, and we're still trying to drive this onboard computer to go do all of our autonomy algorithms. So we don't want to slow that down too much either. So that results in us having, sometimes on the order of 4 to 7 minutes of runtime before we have to go sleep for a while and then wake up at the half-hour mark. So maybe 7 minutes of driving and 23 minutes of cooling off. So yes, definitely want to minimize the time to plan, because the more you're planning, the less time you're doing the actual work of driving around and doing your distributed measurement. And certainly also you want to minimize that time, because anything that you do with the avionics is going to also heat up your system. So it's going to basically speed up how quickly you get to the point where you hit the thermal limit and you have to go to sleep. Let's look at a little bit more of a in-depth look at our rover. So this is what one of our Cadre rovers looks like. If you look at the CAD, it's got a number of sensors for autonomy. So it's got the cameras and the motor controllers, and it's got a a GPR antenna, GPR electronics, and power avionics, and all the kind of stuff that you expect a rover to have. And then again, kind of highlighted here is that we have this modal AI voxel. It's a Snapdragon 821. It's got several CPU cores and has a DSP. It's got also a GPU. So quite a capable platform that you can take advantage of. Our flight software is implemented in F prime. It's using C++ 14. We have some reliance on the embedded template library, which covers use cases of when you would use the standard template library, but you do it with static allocated memory. You can also basically, if you have something like a vector, you can give it a fixed size. So you're not doing dynamic memory allocation during runtime. And it's also, we're building this all for the ARMv8 64-bit, though you could also build this for, could do 32-bit builds if you needed to. And we take advantage of the kind of the standard platform optimizations that you get through GCC. This is what our autonomy architecture looks like. I'm not going to go into extreme depth on this, but what I'm talking about today is really one particular autonomy algorithm, which kind of sits at the team planner level. The team planners are typically responsible for kind of solving mostly a multi-agent path planning problem, right? So the strategic planner, which has received a mission or an objective from the ground, is going to say, okay, well, for the next 7 minutes, what we're going to do is a distributed measurement. And then the team planner says, okay, well, let's look at what the world looks like. Let's look where the robots are and figure out what to do with the robots. And then those trajectories that it generates get passed down to the onboard planner, which works with the surface mobility system to get the robots to move. So more specifically for the distributed measurement, what we're doing is that we have a requirement for this GPR to work as a virtual instrument, this ground penetrating radar. All of our robots have to be in specific physical locations and usually defined by some sort of offset with respect to each other. And they have to maintain that as they traverse through the environment. And you're allowed to have some small deviation, so your algorithm can reason about, well, let's give the robots a little bit of slack so that they can move around obstacles, but they don't want to deviate too much because then you're impacting the signal-to-noise ratio of your ground-penetrating radar, and you don't want to do that. And then in general, the only thing that it's being told is this formation that they're supposed to keep and a sort of a nominal trajectory for the path. So we're not telling the robots from the ground individually what they should do, but this algorithm takes kind of a specification for the team and outputs the paths. So if we dive even deeper into the software, our pipeline roughly looks like this, and it has these 3 key components. There's really a pre-processing step, which is we take the map and we perform something called an obstacle inflation on it so that the planner has an easier problem to solve. But that operates directly on the map and has to perform a mathematical operation on most of the cells that are within that map, and that can be expensive. And then sort of highlighted in gray is the actual sample-based motion path planner, which I'm not going to talk about. But basically what it does is figures out, okay, what are feasible solutions in the space, and how do I connect these to get the robots from point A to point B? And then that's also then again post-processed, because usually with these planning algorithms, you might get something that's a little bit of a little bit jagged, and it doesn't necessarily fit the dynamics of the system perfectly. So we do some post-processing, which also ends up being not a cheap operation to do. So today I'm going to talk about how we speed up obstacle inflation and trajectory generation. So first, obstacle inflation. So why do we even bother with inflating the obstacles? Well, I alluded to the fact that it makes collision checking for the planner easier, right? Because instead of checking the entire footprint of the robot every time, what you're doing is you're just checking, once you've inflated the obstacles by the size of the footprint of the robot, you just need to check an individual cell. So that speeds up that algorithm, but you still have to go do this inflation. And in this particular diagram, what you're seeing is basically the output of the obstacle inflation. We have an occupancy grid map where Yellow are the obstacles. We have the green, which is the inflation that we want, which is sized by the footprint of the robot. And then everything else is free space, which is, the robots can exist in free space without colliding with any of the obstacles. How do we do obstacle inflation? Well, really, what we need to do is we apply some sized mask, which represents the size of the robot, in which zeros are free space and ones are where the robot actually exists, if it were at that location. And then we have to apply this operator on every single location where there's an obstacle or a cell that's marked as an obstacle within our occupancy grid map. And this mask could be, as in this case, if you do the very conservative approach, you basically make the footprint look like the entire rotated version of the robot. But if you ever want it to be less conservative, meaning you can get closer to obstacles and find more paths through the environment, you actually want to do this on a per rotation basis. So you typically would take the actual footprint of the robot, and then you would do this entire operation, let's say like 36 times, right, for every 10 degrees of rotation. So again, it's fairly straightforward, right? You could envision that this is probably just 2 nested for loops, which is what you would probably implement the very first time you implement it. But that turned out to be rather slow for us, so we looked at ways of speeding that up. What we looked at is OpenCL. And OpenCL is a framework for writing code that you can parallelize. So for loops, we can typically, are pretty good candidates for doing some sort of parallelization. What's really nice about OpenCL is that it's designed for you to be able to address a multitude of different heterogeneous compute devices. So this could be the CPUs, this could be the DSPs, this could be the GPUs, so long as somebody's written basically a driver for you to do it, to access that device. And as I mentioned before, the voxel doesn't just have a CPU, and it has a GPU. So we were thinking, well, maybe if we offload this operation onto the GPU can just do this in parallel very, very quickly. Typically, what you do with when you write an OpenCL program, what you're doing is you're writing a kernel that describes some sort of operation. Then basically, in our case, that would be if we had this obstacle inflation kernel, every time in the map there is a occupied cell, you go and apply the footprint. And then this is executed this is basically compiled and then executed in parallel over however many compute units your device has. In the case of the GPU, I believe it had 4 compute units on the voxel GPU. So we'll do this 4 times in parallel. And also a good thing to remember is you can also do this with CPUs. There's a library called libpocl, which allows you to do this on a CPU as well. I've actually tested this algorithm not on just our target platform, but on an NVIDIA Jetson. So I was able to compare what libpocl would do with OpenCL on the CPU versus using OpenCL to target the Jetson's GPU. And then finally, you also get fine-grained control over how you deal with memory, so you can still obey your flight software rules about not doing dynamic memory allocation. You can actually externally and statically allocate your memory and make that accessible to the GPU, either through copy operations, or you can pass it. You basically pass it in a pointer, and it can access the memory directly. So what does that look like? So what it really happens is that you end up getting a parallelization of this operation, right? So instead of just doing this row by row, you get to have multiple compute units do this, and you also get to take advantage of some other nicenesses of the GPU itself. And also, this happens to be pretty fast because your operations don't have to be atomic, right? So long as you just write down into the memory location that there's an inflation zone, that holds, right? You don't have to worry about making sure that this is atomic. So the results for that were the following. So what we learned is that you do get speed up, but not always. So it's highly dependent upon your problem, right? So if you look at the plots that we have here, what we've done is we've kind of plotted the size of the maps. So the 2 plots are, one is for a 5x5 map, the other is for a 10x10 map. And then what we've done is we've plotted obstacle density, so how much percentage of the map is occupied by an obstacle cell for which you have to do this operation versus the resolution of the cell. So so the higher your resolution is, the more cells you're going to have for that define your obstacle. So down, on the top left, as you would expect, you're not really getting much speed up. So if there's not much work to do, sending it over to the GPU, and it's not going to buy you anything. And I think that makes a whole lot of sense. But there are cases in which you do get quite a bit of speed up, is when you have to deal with a lot of these operations when you're processing your map. So I've called out two particular instances of that. In one case, I show where we don't get a whole lot of speed up. Right, 0.6 is actually slower. It's where we're paying some of the overhead of having to send this over to the GPU. But in that case, it actually doesn't really matter too much, right? Because you're talking about a difference of doing it in 10 milliseconds using OpenCL versus the kind of the regular for loop implementation on the CPU, which took 4 milliseconds. But in the cases where we get significant speed up of, let's say, 10 times or 9.3 times, we're talking about a difference between less than a second for the OpenCL implementation and 7 seconds for the for loops. And as I said before, that's just for one round of this obstacle inflation, right? And if you are trying to do this for multiple orientations, this can add up quite a bit, and you're eating significantly into the budget of time that you have to do your planning for the short cycle. So the other part that I pointed out earlier was the trajectory generation. We figured out a way to also speed that up. It turns out it's a fairly similar operation that we have to do. Really what we have to do to be able to smooth our trajectories is know the distance to the closest obstacle. Because you kind of want to not move your trajectory towards obstacles. You want to keep it away from obstacles so your rovers don't collide with any rocks and the mission ends or the measurement ends. So the way that we did this is that we basically computed the distance to the closest obstacle at every map cell in a way by just applying a cost mask, right? So the mask is just basically the squared distance from that obstacle. And that way, instead of having to, by some mathematical operation, compute where your robot currently is and then search for where the closest obstacle is, you just apply this directly to the obstacles in the map. And you basically get a distance map that you can just look up how far am I away. One limitation of that is that the distance at which you compute this distance is limited. It's finite. It's bounded by the size of the mask, but generally that's okay, right? Because you can say, it doesn't really make a difference of whether I'm 10 centimeters away or if I'm 20 centimeters away. I just care about being anywhere closer than 10 centimeters, and that's the way that you can size your mask. And this made also quite a bit of difference for us because this is a more expensive operation. We have to also do atomic operations. For example, you have to do the max here, right? You can't just simply write whatever the current value is into that cell because that wouldn't make any sense. You have to figure out what is the maximum distance here. And if floats are used, then OpenCL actually also gives you optimized functions to deal with floating point math. So that's another way that you can gain some speed up. So to conclude, I think speed up from parallelizing algorithms or function is it's expected, but I think what we learned through our work is that there's an opportunity to take advantage of hardware that's specialized for this type of work, such as the case for Cadre, where we have an avionics stack that also has GPUs and multi-core CPUs. The implementation of these kernels in OpenCL was incredibly straightforward. We basically took our initial just for loop implementation and took the inner loop and implemented that in OpenCL and got basically a program running on the GPU that did what we did on the CPU in series. And it also is still configurable enough that you can basically make it conform to whatever for flight software rules that you may have. So I think that makes it also a suitable candidate for flight software. And that's it.